So here's another problem. We have a frame, it's called a portal frame by civil engineers, which is basically like a football goalpost, uh, where we have numbered elements like 1, 2, and 3, and the nodes as 1, 2, 3, 4. We can choose any numbering. We have chosen this. Now, uh, in this problem, what we want is this, if these are exactly beam elements, then they would not be able to expand or contract along their own axis. So this is the axis for element number 1, local axis. This is local axis for 2, and this is local axis for 3. So they will not be able to extend or contract along its own local direction. But we want in this case that these elements should be able to expand and contract as well as deform in the transverse direction and rotate about uh, the nodes. To do that, of course, we now therefore, if we go back to the local definition, uh, we go back to the local definition. Now we don't have u1, so we now want to add u1 here and u2 here, which basically means that we now have 6 degrees of freedom per node. We have u1 v1 theta 1, u2 v2 theta 2. U1 and U2 are degrees of freedom that are provided by the truss element. So basically, I am superposing a truss element which has the U1 and U2 at nodes 1 and 2. Now, my local stiffness matrix as a result will become now 6 cross 6 instead of 4 cross 4, which I got from here. Now, how do I do it? I treat it again, the entire element, as a super element composed of a beam and a truss. So what are the degrees of freedom? Degrees of freedom, local degrees of freedom for the truss are 1 and 2. And global degree of freedom for the truss is, the first one is 1. That corresponds to U1. And the second one corresponds to U2, which is actually 4. So I take this global stiffness matrix, and AE by L goes in 1, 1, minus AE by L goes in 1, 4. Again, minus AE by L goes in 4, 1, and A by L goes in 4, 4. So this is, I'm assembling the truss. Then I assemble the beam, and for the beam, the degrees of freedom are 2 and 3 for the first node, 4, 2 and 3, 5 and 6 for the second node. So when I assemble the whole thing, then for example, for my element number 2 here, for my element number 2, which has a length of L, this would be my entire 6 cross 6 element for the beam plus truss, which is also called a frame element. Frame element is actually a combination of a beam plus a truss. So it's 6 cross 6 with 3 degrees of freedom per node. Now, to get the local stiffness matrices in the local coordinate systems for element 1 and 3, I will just have to replace this L by H. The rest of the thing will remain the same, given that AE and EI are same for all the 3 elements. If they were not the same, then I have to take the appropriate values of AE for each element. Now, in the previous problem, both these elements were already oriented in the same direction. So the local stiffness directions are same as the global ones. So we did not have to rotate the coordinates. But in this case, these two elements are vertical and this one is horizontal. So this one is located, this one's axis is located along the global axis, but these are rotated. This is not a big deal because we now have to, for elements 1 and 3, we will have to take the global stiffness, take its local stiffness matrix in the local coordinate system and transform it into the global coordinate system. We have already done this for the truss, and for the beam or the frame, we do it in pretty much the same way. We have, for example, degrees of freedom 1 at node number 1, we have degree of freedom 1 equal to u1, 2 equal to v1, and 3 equal to theta 1. And if the node number of this is n1 and global node number of this is n2, then the global degrees of freedom at this, remember there are 3 degrees of freedom per node. The first one will be u 3n1 minus 1. The second one, which is along y direction, will be u 3n1 minus 2. Sorry, this is 3n1 minus 2. This is 3n1 minus 1. And this one would be u3n1. So 3n1 is a rotation. And similarly here, you would have this as u3n2 minus 2. This as u3n2 minus 1, and this you will have u3n2. So these are the global coordinates. For node number 1, if you transform u1 v1 to u3n minus 1, u3n1 minus 2 and u3n1 minus 1 by an angle phi. So cos phi sin phi minus sin phi cos phi is what you get. Theta 1 is not transformed. Remember, u3n1 is a rotation and same as theta 1. So this remains 1. This is not transformed. So theta 1 is equal to u3n1. And the transformation matrix here is 3 cross 3 transformation matrix we call T. This rotation was not there in case of truss, and you had got this 2 cross 2 transformation matrix only. In this case, you get a 3 cross 3 one, and you have to do this for node number 1 as well as node number 2. So to do that, this U is your global set of global degrees of freedom. And this U is the set of local degrees of freedom. Right? And this entire matrix that transforms all the local degrees of freedom to the global degrees of freedom is written as capital T, as in the case of the truss. So for a generic element E rotated by an angle phi with respect to the global axis, the local stiffness matrix in the global coordinate system is T transpose KLT, just like in case of the truss. And in our problem, phi is equal to 90 degrees for element 1 and 3 and 0 degree for element 2. And also we will have u1, u2, u3, u10, u11 and u12 equal to 0, because these are all built in. So these are degrees of freedom 1, 2, 3, and these are degrees of freedom 12, 11 and 10. So all these are set to 0, and you have a load applied at degree of freedom 1, the first degree of freedom, that is 1, 2, 3, fourth degree of freedom in the global system in the positive x direction. So the force vector would be this, with the load applied at the fourth degree of freedom, and there's a moment also applied. There's a moment also applied at degree of freedom. This is fourth, fifth, sixth, seventh, eighth, ninth degree of freedom. So at the ninth degree of freedom, you have a moment applied. So this is the moment at 9th degree of freedom. This is your entire generalized force vector. You will have to put in these values and change your global stiffness matrix. First, you will have to take this, assemble into global, then put these values into the global stiffness matrix and modify it. This is your force, then solve for it, and you get all the rotations and displacements at the nodes. Now, once you have got the rotations and displacements, again you go back to each element, take the nodal displacements for that element, and you can find the stresses and moments, forces and moments all over the element in any element you like. So that process we have done for the previous problem. We are not going to do this for this problem. It will be complicated, but you can start writing a small code to solve this problem. Give some values to EI and L cube, EI and L, and solve you have to give EA and EI both, and give some properties and try to see if you can solve a problem, solve the portal frame problem with these boundary conditions and forces applied. Okay,